In this lecture, we are going to derive the expression for half power frequency in a RLC circuit. So this we can abbreviate as HPF. Okay, so what is the first question? We have to understand what is meant by half power frequency, right? So first, if you take a series RLC circuit, that means all of the components are in series connection. So let this be Vm angle theta. So we will take the maximum value to represent the magnitude. Whenever we are representing the magnitude and phase, we can use either the maximum value or the RMS value. Okay, so here we are using the maximum value. In general, if nothing else is specified, then you can take it by default as RMS value. Okay, so now we have the components R, L and C. So now, depending on the frequency of this voltage source, we are going to get different responses of the circuit, right? So that means this is Vm angle theta, means that it is Vm sine omega t plus theta, right? Or cos omega t plus theta. The point is, this frequency here, when you vary this frequency, then you are going to get a different characteristics. If we plot that on the graph, it will be frequency characteristics. So we can plot the current, that means what is the current variation with respect to frequency, what is the impedance variation with respect to frequency, or the voltage across each of the components, right? So all of this is called the frequency response. Now what happens at a particular frequency? We have the resonance condition, right? So at resonance condition, we have the reactance to be 0. At resonant frequency, which we can take as omega r or omega naught, the reactance X is equal to 0. So that means the inductive reactance is equal to the capacitive reactance. This is the condition at which the impedance value is minimum in the circuit, and so the current drawn from the source will be maximum. Okay, so this is resonant frequency. Now we want to discuss half power frequency. Okay, so what is this half power frequency? It is simply the frequency at which power dissipated in the resistor is equal to half of the maximum power that can be dissipated. Okay, so when will the maximum power be dissipated? When the circuit is at resonance. Why? Because at resonance, the maximum current is going to flow in the circuit. So we can write this as half of the power dissipated at resonance condition. Okay, so why is this? Because current at resonance is maximum. When current is maximum, power dissipated is also maximum. So this is what is half power frequency. So we will now try to derive the expression. So how to derive the expression? We will make use of this expression. So first we have to know what is the power dissipated at resonance. We will call this as P max. So power dissipated at resonance, P max. This is going to be equal to Vm square by 2R. Why is that? We know the power is equal to the RMS current whole square into R. So this is going to be, we can write in terms of maximum values as Im by root 2 whole square into R. And at resonance, we have the current to be equal to Vm by R. Why is that? Because the reactance is 0. Okay. So at resonance, Im will be equal to Vm by R. So we have Vm by root 2R whole square into R. Okay. So that is how you are getting this expression, Vm square by 2R. So this means that the power at half power frequency, power dissipated at half power frequency, this is going to be equal to half of P max, which is Vm square by 4R. Next we can also, you can take it as the first equation. Okay. And the half power frequency we can also express in terms of the current at half power frequency, right? So this is going to be half, you can take it as IH square into R, where IH is the current at half power frequency. So this, if you take as equation 2, equating 1 and 2, we have half IH square into R is equal to Vm square by 4R. So we are trying to find the expression for the half power current. So we will get that as IH is equal to Vm by root 2 into R, right? So now we have the expression for half power current. From here we can get the impedance at half power frequency. ZH you can take, this is going to be Vm by IH. The voltage is going to be the same because it is the source voltage. So here we will consider only the magnitude because we don't know anything about the phase condition. We are not considering the phase condition. Okay. So the impedance you can get as Vm by root 2R. Okay. So this is magnitude of Z, which you are going to get root 2R. So in terms of R and X, if you write, the magnitude is going to be root over R square plus X square. This is equal to root 2R. So you're going to get R square plus omega L minus 1 by omega C whole square is equal to 2R square. Okay. So you're going to get omega L minus 1 by omega C is equal to plus or minus R, right? So from here you're going to get two quadratic equations. So if you rearrange, you're going to get omega square minus omega R by L minus 1 by LC is equal to 0. This is one equation, and the other equation is omega square plus omega R by L minus 1 by LC is equal to 0, right? So from each of the equations you're going to get two expressions. Okay, so from here you're going to get omega is equal to plus R by L plus or minus root over R by L whole square plus 4 by LC by 2, and from here you're going to get omega is equal to minus R by L plus or minus R by L whole square plus 4 by LC divided by 2. Now here the important point is the frequency can only be positive. Okay, frequency can only be positive value. Negative value we cannot take. So we have to take the positive values only from the 4 available values. We have 4 different values here, right? So here if you see R by L and R by L is here. If you take this term R by L whole square plus 4 by LC, which is greater than this term. Okay. So if you take the positive value, no problem. But if you take the negative value, then the negative term is going to be bigger. So we cannot take that particular value, right? So we have from the first equation we have only one value, plus R by L plus root over, you can in fact write 2 also here. So inside it will become R by 2L whole square plus 1 by LC. Okay, so this is one expression. Similarly, with the same funda, if you see here, you're going to get this term is greater than this term. So if you take the positive value, then it is going to be positive value. But if it is negative, then both terms will be negative. So that is not a valid option. So you have omega is equal to minus R by L plus R by 2L plus root over R by 2L whole square plus 1 by LC. Okay, so we have two different values and both of them are half power frequencies. We have two frequencies at which half power occurs. Okay, so we can represent them as simply omega 1 and omega 2, which is going to be, the smaller value is going to be minus R by 2L plus root over R by 2L whole square plus 1 by LC, and the bigger term is plus R by 2L plus root over R by 2L whole square plus 1 by LC. So in fact, if you experimentally plot the frequency response, that means you have the current as a function of frequency omega. If you plot this, then you are going to get a graph like this. Okay, so this is the resonant frequency. At resonant frequency, you are going to get the maximum value of current that is possible for that circuit. Okay, so you have two values which give you the half power values. The value of current at these frequencies is I max by root 2. Okay, so this we have derived for the series RLC circuit. What about the parallel RLC circuit? So in a parallel RLC circuit, we are going to take a current source and all of the elements are going to be connected in parallel, R, L and C. Okay, so when we take a voltage source, then we cannot study the frequency response because the voltage across all the elements in a parallel circuit is the same. So when we take a current source and we vary the frequency of the source, then we can study the behavior of the circuit. Okay, so this is why we take a current source. So now what is the half power frequency? It is the frequency at which the power dissipated in this resistor is half of the maximum power. Okay, so maximum power is power at resonance. So what will be the power at resonance? P max is going to be equal to Im square R by 2. So how do we get this expression? The power dissipated in the resistor is equal to the voltage across the resistor by Vm square by R. We have to write 2R because this is the maximum value and not the RMS value. Okay, so at resonance what happens? The reactance is going to be 0. All of the current is going to flow into the resistance only. So you are going to have the voltage is equal to Im into R whole square by 2R. Okay, so that's how you're going to get Im square R by 2. So this is the P max value. Then what will be the half power frequency? This is going to be P max by 2, which is Im square R by 4. Now at half power frequency, we can also express in terms of the voltage. So VH square divided by 2 times R. This is going to be equal to this value, Im square R by 4. Okay, so you're going to get the voltage across the resistor, all the elements in fact, this is going to be Im into R by root 2. Okay. So now from here we can find out the impedance or the admittance value. Okay. So we have the impedance which is equal to VH by Im. This is going to be R by root 2. So in a parallel circuit, it is easier to deal with the admittance value. So we are going to take the admittance instead. We have admittance is simply the inverse of impedance, the magnitude, right? So this is going to be root 2 by R. Okay, so the admittance value we have got. Now what is the admittance of the actual parallel RLC circuit? Admittance of the parallel RLC circuit. This is going to be the sum of admittances of each of the elements. So 1 by R plus 1 by j omega L plus j omega C. So this is going to be 1 by R plus j times omega C minus omega L. So this is the admittance. So the magnitude we can equate from these both expressions. So we are going to have 1 by R whole square plus omega C minus omega L whole square is equal to 2 by R square. Okay. So from here it is sort of a similar process, right? Omega C minus 1 by omega L is equal to plus or minus 1 by R. So now we have two quadratic expressions. So what are the two quadratic expressions? If you rearrange the terms, you're going to get omega square plus omega by RC minus 1 by LC is equal to 0, and the other equation is omega square minus omega by RC minus 1 by LC is equal to 0. So from here you're going to get four different values of frequency. So what will be the first set of values? Omega is equal to minus 1 by 2 RC plus or minus root over 1 by 2 RC whole square plus 1 by LC, and the other set of values is 1 by 2 RC plus or minus root over 1 by 2 RC whole square plus 1 by LC. So once again you can see that this term is equal to this term. So the term underneath the square root is bigger than this term. Okay. So if you take the negative value, both will be negative values. So only the positive value we have to take because frequency should be positive. If you take the positive value, this term is bigger than this term. So the frequency will be positive, right? So you're going to get omega is equal to minus 1 by 2 RC plus root over 1 by 2 RC whole square plus 1 by LC, and the other term is going to be 1 by 2 RC. You have to take the positive sign here. Negative term, negative sign will give you negative frequency. So 1 by 2 RC whole square plus 1 by LC. So this expression is very similar to the one that we got for series RLC circuit. The only difference is here the 1 by RC term here in all the four places. That 1 by RC is simply going to be replaced by R by L. That's it. Instead of R by L, we have 1 by RC here. Okay. So this is the expression for half power frequency.